Hi everyone, my name is Ahmed, Sales and Marketing Director at Samsung Electro-Mechanics Europe. In a previous training video, we discussed the notion of insulation resistance and dissipation factor. And today, we're going to discuss a new concept, which is DC bias. This is our fifth educational content that you will find online, and there are more to come, so stay tuned for new releases. Now, let's begin today with a quick question. If a DC voltage is applied to a ceramic capacitor, will the capacitance value change or remain the same? You will be surprised that both answers are correct, and in this video we will discuss why. As you can see in the graph, MLCCs made of class 2, that means X7R and X5R material, with high permittivity may have high capacitance, but their capacitance decreases as DC voltage is applied. On the other hand, MLCC made of class 1, example C0G material with low permittivity have low capacitance. But as shown in the graph, capacitance is constant as DC voltage is applied, with very little change. In the next slide, let's take a closer look at the principal characteristics of DC bias. What you see here is a simple capacitor model with dielectric layer inserted between two metal plates. There are many dipoles inside the high dielectric constant material layer. If the AC voltage is applied here, dipoles are oriented according to the direction of the voltage applied. If it is well oriented according to the direction of the AC voltage, it has a high dielectric constant and the capacitance of the capacitor can be made high. With no DC voltage, there is no interference to dipole inside the dielectric layer, which are able to move freely depending on AC voltage. In this case, permittivity is normal and there is no change in capacitance. Now we will apply a little DC voltage between the two plates. When the DC voltage is applied, you can see in the lower graph that the level of the entire AC voltage is offset by the DC voltage amount. When the DC voltage is applied, the dipoles receive electric force in the direction of the DC electric field, which interferes with the direction change according to the AC voltage direction. Unlike the previous screen, you can see that the degree of movement of the dipoles has decreased substantially. As the movement of the dipole decreases, the permittivity decreases and the capacitance of the MLCC decreases accordingly. Now, let's apply a greater amount of DC voltage between the two plates. The level of total voltage has been further offset by the DC voltage. It can be seen that the movement of the dipoles is further hindered by the strong DC electric field, and the movement of the dipoles is significantly reduced. In other words, the permittivity becomes smaller and the capacitance of the MLCC is subsequently lower. So far, we've seen how MLCC capacitance decreases when a DC voltage is applied. We've demonstrated how the electric field caused by the DC voltage interferes with the movement of the dipole and decreases the material permittivity, causing the DC bias phenomena. That's all for now. Thank you very much for watching, and check our website for our latest educational video at www.samsungsem.com.